So in chapter 13, this is the solutions chapter, and if you remember, a solution is a homogeneous mixture. So when you look at a homogeneous mixture, it has uniform composition throughout. They're usually clear when we think about solutions. That is, you don't see particulate, and there doesn't seem to be anything blocking your view. Now, it could be colored. It could be a red solution or a white solution, or it could be, well, I guess not white, but colorless solution, or it could be blue, or the things like that. But it is homogeneous. It's clear. Okay. And then along with solutions, you have to learn some terms. So we talk about the solute. Solute is the thing being dissolved. It's usually the lesser quantity material, and it is the thing being dissolved. Now, in a solution, we have the solute and the solvent, and the solvent is usually what's in greater quantity, and it's doing the dissolving. So when you think about, for example, water and salt, water is usually in greater quantity and it does the dissolving. So we think about that in those terms as water being the solvent. Now, the concentration is defined in a lot of different ways in the sciences. And in particular, it's the quantity of solute and then it's over some property of the solution. So it could be quantity of solution. Could sometimes be quantity of the solvent. And then depending on the way we define the quantity, that'll give us different units. But when we talk about concentration, we think of things being either being concentrated or dilute. So when we say concentrated, it has a high amount of solute per volume or mass, and then we have dilute. And dilute, these are relative terms. So if you have a lot of material, we usually say it's concentrated. And if we have a very little bit of material in the solution, then we usually say it's dilute. Now, as you make solutions, you have to add the solute to the solvent, and at some point, for most solutes, not all solutes, but for most solutes, you reach a point at which you can't dissolve any more material. And so we call this the solubility or the solubility limit. So the solubility limit is the maximum amount of solute that is dissolved, that can be dissolved in a solution and still be stable. I'll explain that to you in a second. Okay, so what does that mean? It means it won't precipitate. It means stuff doesn't come out of solution. So, for example, if you have sugar and you heat it up, you can get sugar to dissolve in water. But then if you let it cool down, then what happens, so you're heating it up and you dissolve a lot of sugar. If you let it cool down, crystals will come out of the solution, and that's how we make rock candy, and that's a precipitate that's coming out. And that solution wasn't stable as you lowered the temperature, so solid had to precipitate out of the solution. So we call that the solubility or the solubility limit. Now, a term that goes along with that is a saturated solution. This is at the solubility limit, and this is a very temperature dependent phenomenon usually, and then there's unsaturated. This is below the solubility limit. Now there's another term, it's called the supersaturated solution, and these are unstable solutions and their concentrations are above the solubility limit. So a lot of terms, and there's actually one more besides concentrated and dilute and the solubility limit. There are some substances that you can mix together in any proportions, for example, water and alcohol, and those are solutions that we say are miscible. And this means mix in any proportion. Now there's also the word immiscible, I-M-M, I-S-C-I-B-L-E, immiscible. You hear that a little bit less, but in an immiscible solution, you can't mix it in any proportion. So miscible means any proportion of solute and solvent can be put together, and an immiscible means at any combination you can't make a solution. So there's a lot of different kinds of solutions, and it basically goes that you can have a solution made up of any two states of matter, where one is the solute and one is the solvent. So, for example, a gas in gas, most common example of this kind of solution is air. So air, when we say air is 80% nitrogen and 20%, roughly, there's other components, but if we said we had a gas mixture, 80% nitrogen and 20% oxygen, the solute would be nitrogen, or the solvent would be nitrogen, and the solute would be oxygen in that case. You could also have gases in liquids, so you could have oxygen dissolved in water, and of course the oxygen is the solute and the water is the solvent, right? That's how fish get their oxygen, for example. But carbon dioxide dissolves in water. Like in a soda, you can have CO2 dissolved in water to make a carbonated beverage. There's another equilibrium with carbonic acid in there, but you have CO2 dissolved in the water. That's a solution. You could have liquid, so water, ethanol, so like a mixed drink, like when people go to bars and they order I don't know, they order drinks. I don't really know any names for drinks. But let's say they order a drink and it has alcohol and water in it. That's a solution. Usually the alcohol, right? Alcohol is ethanol. We say alcohol, that's the alcohol that people drink. That's ethanol is the solute, and the solvent is usually water. In fact, it's usually well over half the volume of the solution is water. Now, solids and liquids are some of the more common types that we think about. So salt water, for example, seawater, or sugar water, when you put sugar in coffee, for example, that would be an example of a solution of a solid in a liquid solvent. So that would be, for example, sucrose, that's table sugar, in water. Right, the sucrose is the solute and the water is the solvent. And then you can have solids in solids, and in engineering we call these alloys. And so brass is an alloy of copper and zinc, but there are stainless steels that have chromium or other metals dissolved homogeneously throughout their structure, and so we would call those solutions as well. The only type we don't list here are liquids in solids, because the solid is almost always considered the solute in those conditions. So real briefly, I want to talk about some of the things that affect a substance's ability to form a solution with another substance. Okay, so the first thing that comes to mind as a chemist is intermolecular forces. So remember, there are different kinds of intermolecular forces, but there are ion intermolecular forces, so we call them ionic forces. And we didn't really talk about those in previous chapter, but those are ionic bonds, for example. Then there's a hydrogen bonding. And then we have dipole-dipole. And then we have induced dipoles, or we call van der Waals forces, but I prefer to call them induced dipoles. There's supposed to be an I in there. I think I've missed it. So anyways, but it doesn't matter. So here's the thing. The more, and the way I put these, listed them here, these are the most similar, most polar, most charged on this end. And these are the least charged. And so, well, this word is charged, sorry. Okay, so here's the thing. Substances that are highly charged will dissolve each other. So stuff that's ionic and hydrogen bonding will dissolve. Ionic and dipole will dissolve to some extent, but ionic compounds in non-polar, remember induced dipoles, these are compounds that are non-polar. Those won't form solutions at all. So ionic compounds can be dissolved in hydrogen bonding solvents and to some extent in dipole-dipole interacting solvents, things that don't have hydrogen bonding but are somewhat polar, but you can't make them with induced dipoles. On the other hand, things that are hydrogen bonding can make solutions with things with dipoles, but again, things without any charge in them, without any dipoles, won't dissolve most things that are hydrogen bonding. So in general, the stuff that's charged, the more alike that it is, the more miscible those two will be, and the least alike that things are, the less less probability there will be that they'll form a solution. So on this end we have polar compounds, right? On this end we have nonpolar, and the nonpolar compounds, a big class of them, and I'll show you down here in this little table, a big class of nonpolar compounds are like these. These are the hydrocarbons. Or things, sometimes large molecules with lots of hydrocarbon, but only one polar section, because this makes it polar in here. These kinds of molecules tend to be mostly nonpolar, so we consider them to be nonpolar solvents, and they tend not to dissolve things that are more polar. So like dissolves like refers to the intermolecular forces, and then we can break it down into ionic kind of forces, hydrogen bonding, dipole-dipole, and things that lack dipoles or that have induced dipoles. All right. Another thing that affects solubility is temperature, and it affects that in different ways depending on the type of solution that it is. So if you have a solid in a liquid, okay, this is the solute and this is the solvent, and then you have temperature going in this direction, increasing temperature going to the right, and then we have solubility going in this direction, so solubility. Remember, solubility is the amount of material that you can get dissolved into a given amount of solvent. In general, for most solid liquids, it goes like this, or it at least goes in the upward direction. A few, and a very few, go in the opposite direction. So like this, so there's a few that go like this, and this is most of them, okay, increase with temperature. What this means is as you increase the temperature on this axis going that way, then the solubility goes up along that axis. Now, like I said, for a few it goes down, but we won't spend a lot of time on that. Now, for gases, it turns out gases all decrease in solubility as temperature increases. Because really what gases want to do as you increase the temperature, they want to become, they want to expand, or they want to have more kinetic energy, so they want to be free of the solution, and so they tend to move from the solution phase to the gas phase. Now, pressure also has an effect on gas-liquid equilibrium. And as pressure increases, so let's say you have a container that looks like this, and I have a solution in here, and then I have, let's say, CO2 gas, and it's at 1 atmosphere. There's going to be a solubility in this solution, and I'll just call it S. Okay? If you change the pressure in the container, so now I have CO2 at 2 atmospheres, then the solubility doubles, so now it's twice as much. Okay, so solubility increases in proportion to pressure. So if you have CO2, for example, and you open up a soda, right? CO2 is the gas that comes out. If you pressurize the container with CO2 and then seal it, so sometimes they have these stoppers that you can stick in and actually pump CO2 in, then you can increase the solubility of carbon dioxide in the water, and the CO2 goes back into solution and stays in the solution. And doesn't go flat, is what that eventually means. Okay, so here's an example of a problem. It says pick an appropriate solvent from table 13.2. So this is what this table is, to dissolve the following. So this says motor oil is nonpolar, right? So if all you know about it is that it's nonpolar, then an appropriate solvent could be hexane. It could be toluene, or it could be possibly diethyl ether. Now, on the other hand, sugar is polar, and so the types of solvents that you could choose for sugar would be those that are polar, and so those would be things like H2O. In fact, if you use your common sense on that one, you know you can dissolve sugar in water, so that would probably be your first choice. Lard, fat, right, is nonpolar, so again, you could have chosen one of these. And then potassium chloride is ionic, and remember in our scale, ionic is closer to polar and hydrogen bonding. So potassium chloride would most likely be most soluble in water. If you remember, water is a hydrogen bonding solvent. So that's probably the best choice out of that list. Acetone, you can't dissolve very much acetone, but in methyl alcohol you might be able to dissolve a little bit more because it's also very hydrogen bonding solvent. So I'd like to review an important topic from previous chapters, and that's the topic of electrolytes. So electrolytes give a solution the ability to carry an electric charge, and the way we learned about these initially is when we talked about soluble ionic compounds. So there's the concept, strong electrolytes, these make many ions. Okay, so these are things like soluble ionic compounds. And what happens when an ionic compound dissolves in water is it splits completely into its cations and its anions, and that gives it the ability to have these positive and negative charges to carry the electrical current. Now, we also have strong acids that are part of the group of compounds that are strong electrolytes. For example, if I have HCl and I put that into water, that forms H plus and Cl minus, just like if I took sodium chloride aqueous and looked at what it actually was, it's actually sodium ions and chloride ions like that. Now, we have weak electrolytes, and these make few ions. And in particular, the kinds of compounds that we're looking at that were weak electrolytes are the weak bases, or the weak acids, sorry. And there's also weak bases, but we don't cover those in this class. But we could talk about weak acids. And a weak acid is something like HF. And when you put HF in solution, you still make H plus and F minus, but the difference is 99% of it is still as HF, whereas when you look at a strong acid, less than 1% typically is left. So this would be greater than 99% H plus and Cl minus. The last type of compound that's important in this concept of electrolytes are the non-electrolytes, and these make no ions. So what we mean by that is when they go in solution, they don't make ions, and these are things typically that are molecular compounds. So, for example, methanol is a non-electrolyte. Now, why is methanol different than, let's say, a strong electrolyte like NaOH? All right, and to remember that when we're talking about ionic compounds, we have a metal and a nonmetal. And then when we're talking molecular compounds, these are all nonmetals. The exception to that is actually the acids. Acids are generally molecular compounds, because you'll notice like HCl, there's no metal there. HF, there's no metal there. But they're the exception to the molecular compounds being mostly molecular compounds. They're the ones that make ions when you put them in solution. Okay, so now what I'd like to do is talk about solution concentration. There are different units that we use for solution concentration, but one of the important ones is percent by mass. So this is going to be the mass of the solute divided by the mass of the solution. Now remember, the solution is both the solute plus the solvent. And then we multiply it times 100 to give us a percent, or a per 100. Okay, so let's look at how you would do that calculation. If I have 0.2 grams of sodium chloride in 155 grams of water, that would be, the solute would be sodium chloride, so it would be 0.2 grams. And then the solution wouldn't be 0.2 or 155, it would be 155.2. It would be the combination of those two, like that. And then we multiply by 100. So when you're given the mass and you're asked to calculate the percent concentration, it's relatively easy. So now I do 0.2 divided by 150.2, or 155.2, sorry. And I multiply that by 100. And this is a 0 point, and I only have one sig fig, so, but I'll go ahead and put 2 and underline the 1. 0.12%. See, 1, 2, because it comes out 1288. All right. So let's go ahead and look at how you might do a couple of these calculations. This is problem 46 out of the 6th edition. And we're going to calculate, for example, the mass percent based on the data that's given. So I have 2.55 grams of solute, and then my solvent mass is 25 grams. So my solution mass is 27.55 with that line underlined. So I should have 3 sig figs. So when I do that, my percent by mass is 2.55 grams divided by 27.55 times 100. Okay. And that comes out to be 9.26%. That's what that equals. Okay, so let's look at a slightly different problem. It says the mass of solvent is this, and the mass percent is this, and we need to calculate the mass of the solute and the mass of the solution. Now, to do these calculations, you go back to the relationships between the solute, the solvent, and the solution in relationship to the percent. Okay, so let's do it something like this. Okay, so I know that I have 45.8 grams of solvent. And I'm going to write out a couple of other relationships. One, I know it's 3.8% solute. But that also means the solvent is 96.2% of the solution. So in other words, right, this plus this has to add up to be 100%. So I looked at the solute percent and said, well, I need to know the mass of the solution or the mass of the solute. Let's go ahead and do the mass of solution first. Okay, so the mass of solvent first, and then I'll show you there's many ways to do this problem. So I have 45.8 grams of solvent. And then percent, right? 96.2 grams of solvent for every 100 grams of solution is what that means. Right? Because when we say percent, it's the mass of the solute for the mass of the solution. But we can also convert that and talk about the mass of the solvent per mass of the solution. And now I use the definition of percent here. And now I can calculate, because grams of solvent will cancel out. And what I'll get is, I get 47.609. Now I have 3 sig figs, so I'll just underline that. That's grams of solution. Now I could also do the grams of solute this way, since I know the mass of solvent, right? And I know the mass of solution, I just subtract the two and I'll get the mass of the solute. So here I have 47.6 grams. But if I want the mass of the solute, it's just going to be mass of solution, 47.609 grams, minus the mass of the solvent, which is 45.8 grams. And that'll tell me how much solute is in the solution. So that gives me 1.81, I rounded, grams of solute. Now, the nice thing about these problems is that anytime that you get one of these, you can always use the numbers you just calculated to get back to the numbers that you were given. So you can sort of, for example, I could take the mass of the solute divided by the mass of solution and see that it comes out to be 3.8%. So now we come to one of the more important units in chemistry called molarity for solution concentration. It's one of the most important units. And that's the number of moles of solute for every liter of solution. You could also write it as N over V to represent moles volume, and moles divided by volume is equal to molarity. Okay, so let's do a quick example calculation. Now, normally you're given concentration or quantities of solute in grams, and then notice here we have the volume of the solution. And so what do I have? Well, if I want to do molarity, right, that's moles per liter. Those are my units. I already have the liters. So I have 0.442 liters. Remember, this is liters of solution. So make sure that that says liters of solution when you do the problem. Occasionally, it'll just say solvent. And in those problems, generally at this level, that's a mistake. And usually, they're assuming that the solution and the solvent are the same volume. Okay, so I need moles. How am I going to calculate moles? Well, I'm given grams. You would calculate this molar mass. So I'm going to say moles, N, is equal to 22.6 grams. And it's 342.30 grams for every 1 mole. And that gives me 0.066023. I'm just going to write 0. With 3 sig figs. So that's underlining this line. I guess the next digit would be a 2, and this is moles. And so I can throw this in here, 0.06602 moles. And so my molarity comes out to be 0.1493 moles per liter. So that would round to 3 sig figs, 0.149, and then M. And so that's the answer for that. Here's another example of a molarity problem. How many moles are in 1.5 liters of 1.2 molar sodium chloride? Now, the first thing I tell my students to do is to go ahead and write this as 1.2 moles per liter. Because once you have the unit, and you notice I put the line all the way across like this to be clear, right? That 1.2 goes with the moles. That tells you how you have to use this in relationship to this. So if I want moles, I'm going to start with 1.5 liters, and then I'm just going to multiply it by 1.2 moles per liter, and that will give me 1.8 moles. So let's look at one more problem, and this is actually problem 76 from your book. It says, what volume of 0.35 molar, so I'm going to say moles per liter, right? That's what I'll write that out. Solution contained 87 grams of magnesium nitrate. So I'm going to write this out as 0.35 moles divided by liters like that. And now I have grams. So that's the number that I'll start with. Now, grams is going to have to get converted into moles. And once I have for moles, then I can convert that into liters. So I want volume, so I'm going to say L, liters. And I'm going to start with 87 grams. And now I got to convert that to moles. So what do you need? You need to go calculate the molar mass. Okay, so I looked it up, and it's 148.32 grams, right, per mole. And that tells me how I will use that in my calculation. So I have 148.32 grams for every 1 mole. And then I have to get rid of, that gives me rid of the grams. Now I got to get rid of moles, so I'll say 0.35 moles per liter. The moles will cancel. And that'll give me the volume of solution that I'll need. And this comes out to be 1.67 liters. Now there's only 2 sig figs in here and only 2 sig figs here. So this will round to 1.7 liters. Actually, this section is a little different than what's in the book. This is more for people who might go on into a job, like work in a factory or work in a company, work in a hospital, in a formulary, and need to make solutions that are mass percents. A lot of times, of course, for real critical things, they'll have a formula for you, and they'll just say, hey, this is how you're going to make the solution, and that's how you make it. But I was going to show you a different way to think about these problems. So let's say you wanted to make a 0.75% solution of sodium chloride, maybe a light saline solution, right? And then I want to have 2.67 grams of sodium. I have 2.67 grams of sodium chloride that I want to turn into that 0.75% solution. So normally what you would do in these kinds of calculations is it says what's the mass of water that needs to be added. But actually in a lab, if you're making this, what you actually do is you calculate the mass of the solution. And I'll explain to you why that is in a second. Now we can get the mass of water from that information and answer this question. But I wanted to do this on a little bit more of a practical note. So if I have 2.67 grams, this is of the solute, right? And then I can calculate the mass of the solution because 0.75% means 0.75 grams of solute. That number always represents solute in the way it's normally presented, right? And then I have for every 100 grams of solution. So notice this calculation is going to give me grams of solution. So when I do that calculation, it gives me 356 grams of solution. Now, to calculate the grams of water you need to add, all you need to do is subtract this from that. But the way this solution would probably get made in a laboratory is you take a beaker. Now, 356 grams is less than half a liter of solution. And you'll take a beaker and you'll put the 2.67 grams in it, and you'll have actually a large balance, and you're just going to add water till the total mass is 356 grams. So you won't actually, when you make the solution, go through the process of measuring the water out. You just know what the total mass is supposed to be. So you add the solid to the beaker, you put it on a balance, and then you just add till the total mass that's in the beaker is 356 grams, and that'll give you the 0.75% solution. Now, molarity solutions, are made in a slightly different way. We want to calculate the mass of sucrose. Now, sucrose was given up here. So this is sucrose, that's its molar mass, 342.3. So that's what we need to know. So we want to make 3 liters of a half molar solution. Now, to calculate the mass of sucrose you need, you're going to go 0.500 moles per liter of solution. All right, and then I have 3 liters of solution, so I'm going to go grams. It's going to be 3.00 liters times 0.500 moles per liter. That'll cancel the liters of solution out, and then we'll go ahead and calculate 342.3 grams per mole, and that'll cancel moles out, and that'll give me my mass of sucrose that I need. And that comes out to be 513.45 grams. So how do we actually make this solution? There's actually a flask. It's called a volumetric flask, and it's shaped like this. It kind of looks like an Erlenmeyer flask, but it has a very skinny neck, and there's one mark on here. And you can get them for different sizes, but 3.00 liters is one of the sizes that you can get. So the way the solution's made is actually you take this solid, you stick it in the flask with the aid of a funnel, or sometimes you have to use the aid of some of the water that's going to go in there. And again, you don't actually measure the water out. You fill the flask up usually about halfway, and you dissolve as much of the solid as you can, and then you go ahead and continue to add water and mix until you get to that line. So most of the time in a work setting, things aren't done the way you learn how to do the calculations. So you're not trying to measure out the water. You just get a flask that's exactly 3.00 liters, and that's how you do that. And for making percent solutions, you never calculate how much water you're putting in. You just calculate the mass of the solution, and you add it to the container to get to the total mass that you need. Another important concept in calculation chemistry is our dilution calculations. It's how do you prepare a less concentrated solution from a more concentrated solution. And so the thing to remember in these problems is that when you're making the solution, adding solvent is how we're doing dilution. It doesn't affect the moles of solute. It just increases the amount of solvent. And so to do these calculations, you have to keep that kind of stuff in mind. So let's say you have a solution, right? And you have 35 mils of a half molar solution, and then you dilute it to 1 liter. So think about a situation, we talked about the volumetric flask, right? You'd have a volumetric flask like this, you'd have a 1 liter flask. That's also a common volume. It would be 1.00 liters. And then you add the 35 milliliters of 0.5 molar. And then what happens is you add water into this, and so it starts out at the bottom. It starts down at the bottom here with a little bit of solution, and then you add water all the way to the top until you get to 1 liter. Okay, so let's talk about how you do this calculation. The first thing you want to do is you want to calculate the moles of this solution. Now, I'll show you a shortcut as well, but I'd really prefer you not use it and learn this concept, because this is the same concept that you'll use for doing dilutions in percent concentration solutions, and there's a couple other units as well that you'll use the same kind of concept to do the calculations. So I have 35 milliliters and 35.0. So I want to calculate the moles that's going to be transferred. So moles is going to be 35.0 milliliters. And then I want to write out molarity again, right? Molarity is 0.500 moles for every liter. Now you'll notice that these units aren't the same, right? So you have to do a conversion in between. So I'm going to go like this. I'll say there's 1,000 milliliters in 1 liter, and then I can cancel the milliliters, and then I can use my molarity, which is 0.500 moles per liter. So the moles that are in that solution come out to be 0.0175 moles. Now, how do I calculate the resulting solution concentration in the new solution for 1 liter? Well, the new molarity, I'll call that molarity 2, okay, is going to be equal to 0.0175 moles, because that number didn't change. And then I'm going to divide it by my volume 2, so I'll call that V2 as I talk about it. I'll divide by V2, which is 1.00 liters. So that still is 0.0175, but now the units are moles per liter. Had that been a 3-liter solution, that top number wouldn't have changed, but the bottom number would have now been 3. Okay, so that's the solution concentration when we do the calculation. Now, let's review really quickly what we did, and we'll come up with a nice little shortcut for doing dilutions. And the shortcut is this. When I did this problem, I took molarity 1 and I multiplied it by volume 1. Now, be careful, right? You have to make sure the units match. And remember, the units that you have to match are the units that are hidden inside molarity. So you'll have to do this kind of stuff before you can use this equation. Okay? So I took molarity 1 times volume 1, and it turns out that's equal to molarity 2 times volume 2. So if I wanted to know molarity 2, what I do is I take, I guess I'll write it over on the right-hand side over here. Molarity 2 is going to be M1V1 over V2 like that. And if you look at the calculation, this is M1 times V1, and that's V2. That's the calculation I actually ended up doing. So that's a convenient shortcut. But remember, it's all traces back to the moles being the same in both solutions. So let's do another problem. It's worded slightly differently, but let's approach it in the same way. It says, what volume should you dilute 25 milliliters, a 12 molar stock solution, okay, to obtain a 0.500 molar HCl solution? So what do I have? Well, where you start these problems always is where you can calculate the moles. And so you need a volume and a molarity. So from these, I'll get the moles. Now, this will be my M1 and my V1. My M2 is this. So what's the problem, right? Again, the same problem that we had in the previous problem, we avoided that we calculated the volume over to liters. Okay, so now let's go ahead and do that calculation. I'm going to say moles. It's going to be 25 milliliters times 1,000 milliliters per liter. Now my molarity is 12 moles, again, per liter. Write it like that. So then you can see your liters will cancel out. So I'll say 12 moles per liter. My milliliters cancel, my liters cancel, I'll be left with moles. And that comes out to 0.30 moles, like that. So I have my moles, but how am I going to calculate from that the volume that I need, right? And the answer again comes in writing this unit out. So 0.5 should be 0.500 moles in a liter. And you notice what you have to do to get those units to cancel out. So I'm going to say my volume, it's actually my V2, is going to be 0.30 moles times 0.500 moles in a liter, like that. So what that leaves me with is 0.60 liters of solution. Now, if you want to verify that the formula works, right, then you're going to go ahead and take your M1V1, and that's equal to M2V2. So this is equal to M2 M2V2. And what do you have to do to get V2 by itself? You have to divide by M2, and that's what we did there. But again, I'm showing you both ways. I prefer the dimensional analysis way, but the formula is very handy as you're getting to learn these things to be able to do these calculations. So you could check when I use the dimensional analysis way, you can go ahead and try the M1V1, M2V2, and see if you get the same answer. Another aspect that we have to deal with is how do you use molarity in solution stoichiometry. And the pattern is very similar. Remember, if you have grams, then you go to grams to moles of something to something else, and then to whatever the quantity is they're asking for in the problem. So for molarity problems, you remember molarity is moles over solution volume. So the molarity is the relationship between these two values. So if you have a volume of A, then you can convert using molarity of A to moles of A. This is still the stoichiometry. And then depending on what you're asked for, maybe you're asked for moles of B, but you may be asked for molarity of B or a volume of B. Then you'll need to know, for example, if you need to know the volume of B, then what you're going to need to be able to do is you're going to need to be able to have the moles, which would come from here, and the molarity of that solution, and that'll allow you to calculate the volume. So rather than talk about this a whole bunch more, I just thought I'd show you an example. So it says determine the volume of 0.225 molar KOH solution required to neutralize each sample of sulfuric acid. So that's what we're neutralizing, means the mole ratio, the moles of potassium hydroxide being used is equal to the moles of sulfuric acid, according to the stoichiometry here. And that gives you the neutralization reaction. So remember, always start with what you can calculate the moles of. So you need a volume, and you need the molarity of sulfuric acid. Okay, so when I'm not going to do A because I don't like that the numbers are the same, but I'll go ahead and do B. So I have a volume again and a molarity, right? So start with your volume, and also what are you looking for, right? We're looking for the volume of KOH. And I can calculate the moles of H2SO4. So I say 185, and this is milliliters. And again, write out 0.125 moles of H2SO4 per liter, like that. So when I do that, I see that these units don't match. And so I have to do a conversion beforehand. So it's 1,000 milliliters for 1 liter. And then 0.125 moles of H2SO4 per liter. So now that'll cancel nicely, right? And this is this part. I've just done this part. I've gotten to moles of A being sulfuric acid in this case. And now what I need to do is figure out moles of B, and that comes from this mole ratio. It's 1 mole of sulfuric acid for every 2 moles of KOH. So I say 1 mole of H2SO4 for every 2 moles of KOH. Now, this is the trickier part, but again, you're given this number. What does that mean? It means 0.225 moles of KOH for every liter of KOH. And so when you look at these units, the moles of H2SO4 cancel. I need to be able to cancel the moles of KOH. So what I'm going to do is go 0.225 moles for every 1 liter. So I have all my units canceled. I end up with a volume, and that number comes out to be 0.20, and then it's 5 repeating, so I'll just round it to 6 because I have 3 sig figs, and that's liters of KOH. Now, KOH. If the problem had asked for milliliters, then you have to be careful. It just says determine the volume. If the answer says milliliters, then you would have one more step here, but it's not actually asking you that in this problem. But if it did, then you would convert it to milliliters. Okay, so I'd like you to try this example now. Give yourself 4 or 5 minutes to try to work this out, but I'll help you get it set up. And so it says, what's the minimum amount of 6 molar H2SO4 necessary to produce 15 grams of hydrogen? Okay, so a minimum amount. What are they meaning by minimum amount? And to start with, we're dealing with a molarity, right? So we have this molarity. So this minimum amount, it goes with this. So for molarity, typically the minimum amount's measured in a volume, right? The other thing is, what do you have in this question? This is the first thing you asked. How do I calculate moles? Or what can I calculate moles of? So for example, if you had a molarity and a volume, that gives you moles, right? So that's one place you can start. What's the other place? Well, the other place is if you have grams, right, you can convert that to moles using the molar mass. And so when you look at this problem, how it's different from the previous one is instead of starting with a volume, we're starting with grams of H2 and we're converting that to moles. So we're looking for a volume. And we're starting with 15 grams of hydrogen. And then the process you're going to go do is this. You're going to go from grams of H2 to moles of H2. And then to moles of H2SO4. And then we need to get to the volume, right? Because we're looking for, again, we're looking for volume. So now we're going to need to go to liters of H2SO4. And the conversion between moles and liters is just like we looked at before, is using the molarity. So I'll go ahead and pause it here. You set it up. Make sure you write all the units out. It's very important that you do that because when you're doing the stoichiometry steps, you got to make sure you know what's on the top and what's on the bottom. So well, you should pause the video. I'm going to write the complete answer out, and then we'll discuss it when you restart the video. So hopefully you got a result that looks like this. The first thing that I did is I needed the molar mass for hydrogen. So I got that, and then I divide by the molar mass of hydrogen to get to moles. And then I used my mole ratios for the 3 and the 2. For the 3 and the, the 3 and the 3, yeah, sorry. And then that allowed me to cancel the grams, the moles, and now I have moles H2SO4. And again, the same trick applies if you're trying to calculate the moles of, the volume H2SO4. Write out the units for molarity like this: 6 moles of H2SO4, and then like this, per liter of H2SO4. And then you can see that, oh, you need to get rid of this, and so the 6 needs to be on the bottom, and then you work it out and you end up with 1.2 liters. Okay, so we'll be talking about something called colligative properties. Colligative properties are properties of solution that depend only on the concentration of the molecules and ions and not the identity of the molecules and ions. So remember, we talked about molarity, right? There's another unit that we talk about in colligative properties, and that's molality. The symbol for molality is a lowercase m. Didn't mean to do that, sorry. So it's an M. And for molality, the units are moles of solute, so the same top numerator, right, as we have for molarity, but the bottom is very different. It's actually kilograms, so it's not a volume, it's a mass of, and then it's solvent. It's not the whole solution. So if you remember in our discussion of molarity is moles per liter of solvent, but for molality it's moles per liter of solution, and for molality it's moles per kilogram of solvent. So the kilogram of solvent is fairly easy to understand. It's just the mass of that. And the moles of solute is relatively easy to understand. But let's look back at the definition. And the definition says properties of solution that are affected by, right, the concentration of solution molecules or ions, and not the identity of the molecules or ions. So for example, if I have ethanol, or methanol. Those are both molecular compounds. They're both soluble, miscible with water. When you put them in water, when you have 1 molal solutions of this or a 1 molal solution of that, doesn't really matter, this or that, the molecular compound, the concentrations of particles is exactly the same. It doesn't matter whether or not it's ethanol or methanol. It only matters that there are 6.022 times 10 to the 23rd particles for every kilogram of the solvent. It becomes especially important if you're talking about ionic compounds, because for an ionic compound, what happens, for example, is sodium chloride, right? We talked about strong and weak electrolytes. Well, sodium chloride is a strong electrolyte because it's a soluble ionic compound. When it dissolves, it's going to give us 2 ions. It'll give us a sodium ion and it'll give us a chloride ion. Now, the molality of a 1 molal sodium chloride solution is the same number of sodium chloride units as there are, for example, in ethanol or methanol, but it breaks up and gives us 2 ions, 2 particles per mole, 2 particles per molecule or formula unit of the compound that we put in there. So molality is dependent on not whether or not if it's ionic or molecular, it's just dependent on how many things those things break up into. So molecular compounds don't break up, ionic compounds will break up. So let's go ahead and calculate the molality of glucose. Glucose is a molecular compound, by the way. And to calculate molality, M is equal to moles, right, per kilogram. And it says calculate the molality of a solution containing 256 grams of glucose and 1.62 liters of water. And then it says assume the density of 1 gram per milliliter. Now, I want you to write this out. This is an important kind of concept to have. If I had 1,000 grams, how many milliliters would that be? Well, if it's 1 gram per milliliter, that would be 1,000 milliliters, right? So one of the important sort of general things to know is that's the same as 1 kilogram per liter, because 1,000 milliliters is a liter and 1,000 grams is a kilogram. So what it's telling us then, if you have 1.62 liters, that's 1.62 kilograms, like that. Okay, so having said that, I can calculate, I have my kilograms, 1.62 kilograms. All I need to do to get the answer for this problem is calculate the moles of glucose. So moles of glucose, we're going to start with 257 grams of glucose. And then if I add all this up, this comes out to 180.0 grams per mole. So I can use that to convert my grams of glucose to moles of glucose. And that number gives 1.42 moles. And it's 427 repeating moles, and it's 3 sig figs like that. So I can write in 1.427 moles with 3 sig figs, and that comes out to 0.881 moles per kilogram, like that. And that is the same as 0.881 m. The way we use the unit m, unfortunately, is the same as the symbol. The same is true for molarity, by the way, but it seems to be more awkward for lowercase m. Okay, so what we'll do next is we'll talk a little bit about the types of colligative properties. I left a little space to sort of outline them, and then we'll do a couple of problems. Okay, so let me outline for you some of the different colligative properties real quick, and then we'll do a problem. So colligative properties. And again, these are properties that change when we add the solute to the solvent. Okay, so colligative. One of them is called a boiling point elevation. Now, one of the important features of the stuff that you're adding, the solute is, we say, non-volatile. That is, it doesn't boil, it doesn't evaporate. So salts, sugars, molecular compounds that fit this category really are things that don't evaporate easily. So when I gave you that example of methanol and ethanol, while those cause a colligative property, they're probably not the best examples because they evaporate fairly quickly. Okay, so one of the things is the solute is non-volatile. And when you add a non-volatile solute to a solvent, we get a boiling point elevation. So for water, right, has a boiling point of 100 degrees Celsius. In fact, we can go like this, I suppose. At 1 atmosphere, a solution, so an aqueous solution, has a boiling point greater than 100 degrees Celsius. That's what the elevation part means. It means the boiling point increases above its normal boiling point. The reasons for this, there's a lot of different sort of hand-waving-ish reasons, but basically it's just because adding the solute makes it harder for the molecules of the solvent to leave the solution. And this is especially true when we have non-volatile solute particles. Now, there's also something called the freezing point depression. So the freezing point of water, right, pure water, is 0.00 degrees Celsius. That's the, sorry, I call it TF. Let's do that. We'll call this TB for that. Okay, so TF is going to be 0.00 degrees Celsius. So if you can get water to 0 degrees Celsius, if you remove energy from the system, it'll turn into ice. And we talked about like the 6.02 kilojoules per mole. We talked about the heat of fusion for ice in the previous chapter. So that extra energy goes into freezing it. But the ice starts to form as soon as you hit 0 degrees Celsius. It'll also start to melt at 0 degrees Celsius if you add energy to it. So if you take an aqueous solution, has a freezing point, I'll call it a TF, less than 0 degrees Celsius. drew Mickey Mouse there, sorry. Yeah, less than 0 degrees Celsius. So in other words, having this, remember when I say solution, it's not just water anymore, but the solute particles that are in the solution prevent the ice from forming. And so in order for to get the ice to form, you have to drop the temperature lower than 0 degrees Celsius. So these are two of the colligative properties in which we can do calculations based off of. And I'll show you the equation, but I'm just going to write a little note here. Delta T is equal to M times K, like this. And then I'll explain to you what that is, but that's how you do the calculation. You'll have a constant, which is K, and you'll have a molality, which you may or may not calculate, but that's M, and you multiply them together, and that'll tell you how much the change in temperature is. So if we're talking boiling point elevation, we just add it to that. If we're talking about freezing point depression, we just subtract it from its normal freezing point, and that's how we get the temperatures, okay? The other colligative properties that we'll talk about, or the other one, I should say, I won't spend a lot of time on all of these, but one of them is osmotic pressure. And I'll spend some time talking about that more. But osmotic pressure has to do with a process called osmosis. And osmosis is the flow of water through a semi-permeable membrane. And in essence, you have a membrane which doesn't allow solute to travel through, but allows water molecules to move through. So think about a membrane like this that has little tiny holes in it, and then solute particles like this that are bigger than the holes, and then the water molecules are these little dots around them. The water molecule can go freely through there, but these larger solute particles can't go through because they're too big, okay? And so having stuff dissolved in solution creates what we call osmotic pressure through a process called osmosis. Okay, so we'll get into that when we go to the lower section, the next page. So let's talk about freezing point depression real quick and how you do the calculation. So water has a freezing point depression constant. So this constant is for water and for any solute that you dissolve into the water. So the question that I wrote here, actually, it's just based off question 100 from your textbook. It says, calculate the freezing point of the solution in problem 100. So we have 257 grams of glucose in 1.62 liters. We got a molality. We know M is equal to 0.881 M, which I hate writing it that way, but that's the way it's written. If I want to calculate the freezing point depression, right, I could go delta TF is equal to 0.881 M times, and then we write out KF like this, 1.86 degrees Celsius divided by M, and so the M's will cancel. So that 1.639, and then it goes on 3 sig figs, so it'll be 1.64 degrees Celsius, right? Now, that's the freezing point depression. That's how much lower the solution boils at, or not freezes at, sorry, freezes at than its normal freezing point. Since water's freezing point is 0 degrees Celsius, then T of the freezing point for the solution is 0 degrees Celsius minus 1.639 degrees Celsius, or just negative 1.64 degrees Celsius. Now, if water's freezing point hadn't been 0 degrees, then it would have been some other temperature, but it's always that much lower, 1.64 degrees Celsius. And it doesn't matter if it was glucose or sucrose or any of those things, as long as the molality of the particles is the same. Okay, we can look at boiling point elevation. The calculation's done exactly the same way. It says calculate the boiling point of the solution in problem 100. And so I'm going to go delta T BP is going to be M, which is 0.881 M. And then I use KBP as 0.512 degrees Celsius over M, so I can get the M's to cancel. Okay, so let's talk a little bit about osmotic pressure. Okay, so think about it like this. If I have my semi-permeable membrane, again, and I don't have anything in there except water. In fact, I could start with water on one side, and then what would happen is, because it's a semi-permeable membrane, right, the water levels would equal out eventually, because really what determines the water levels, let's say I started it like this, right, then what would happen? Well, eventually this one would drop, and if the chambers are the same size, it would drop to half its height and stop. And the reason it would stop is because on the other half you have water levels that are like that. So this is initially, and this is at equilibrium. And what's happening here actually is the water molecules are still going through like this, but the rate at which they travel back and forth is the same. And so even though there's exchange and movement of molecules, the levels don't change. And they can in fact show that this kind of behavior happens by taking radioactive water molecules basically and putting them on one side and once it's at equilibrium, and then you can see the movement of the particles, the radioactivity increase on the right hand side. If they stick it on the left hand side, you can see radioactivity increase on the right hand side as the water molecules go through, even though the levels don't change. Okay, so what happens when you put particles in here, right? So this would be the next step. So what I'm going to do, rather than redrawing on the drawing I already drew, I am going to cheat big time. I am just going to copy that and move it over here. Okay, so now what I'm going to do, I don't know if it'll let me erase this. I have it, it looks like this. This is my new initial. Oops, I got to put a pen up here. This is my new initial. So equilibrium takes place. I get my new initial, and then I add particles to, and this is where I would ask the class which side, but I'll put them on the left side because that's just the way I am. Go like that. So I have these particles distributed, right? Non-volatile solute particles. Sugar, in plants this would be sugar, and this semi-permeable membrane would be the cell wall. But what will happen in this case is the particles restrict the flow towards the right, and what happens is this gets shorter, whereas on the right hand side it doesn't change. So now I'm not at equilibrium anymore. I have a net flow in this direction. So because I have a net flow to the left, what's going to happen is this level will rise, right? And the levels will be different, and what I'll do is I'll use a red pen to indicate that, like this. And what stops the flow of water? What stops the flow of the water is the pressure above that level there. So this is actually, when you have water like this, the pressure stops the flow. And that's pressure is what we call the osmotic pressure. Now this is not for this class, but just so you see this, that pressure, right, is N over V times RT. This is how we calculate the osmotic pressure. It's actually, this is the molarity. And so ideal gas law can actually be used to calculate how much pressure is going to be created based on the molarity of the solution. Okay, so a couple of terms that are important here, right? We have isotonic, we have hypertonic, and we have hypotonic. Okay, so in this scenario, this was the hypertonic side on the left. And this side is the hypotonic. And so the idea is remember, the particles don't move, but the solvent moves. So the solvent moves from the side of lower concentration, in this case it's 0, to the side of higher concentration. In essence, this liquid on this side of the diagram is trying to dilute these particles down to 0, basically, is what it's trying to do. Now, isotonic would be this situation. Now I'm going to do this. Probably shouldn't. Let's say that represents the concentration. Those would have the same osmotic pressure, and so those would be isotonic. And so even though you, in essence, slowed down the flow of solution from one side to the other side, you've also equally slowed it down in the other direction, and so we have no net fluid flow. There's not a net flow like I've shown over here. So that would be isotonic when there's no net fluid flow. And fluid flow always goes from the hypertonic to the hypotonic side, trying to lower the solute concentration. Now, you might be interested to know there's a couple of other properties that we didn't talk about in this section, that are related to intermolecular forces. And it's usually brought up in this area, but those are capillary action. And so if you're interested, you can look that up, and I can talk to you about it. But oftentimes in the section where they talk about these things in textbooks, they often talk about capillary action, along with the intermolecular forces and other things. All right, well, that's it for the chapter. If you have any questions, as always, just feel free to contact me.